Welcome back to the UAV Understanding Drone course. In the previous lecture, we learned about the first category of sensors used in drone designing. Now in this lecture, we will learn about the second and third sensor types. GNSS, Global Navigation Satellite System. It measures the drone's location by calculating how far it is from predefined satellites such as GPS, Galileo, GLONASS, etc. The GNSS data provides inputs to a drone, allowing it to maintain position, return to home, or follow a series of preset waypoints. GNSS receiver chips receive satellite data and process it in order to work out position, velocity, and time. Other sensors such as IMUs and barometers are combined with the GNSS to improve the drone's accuracy. Light detection and ranging. It measures the reflection time of a pulsed laser beam for navigation and collision avoidance purposes as well as for mapping and other imaging applications. Infrared and thermal sensors. The potential use for infrared sensors, especially in cameras, are vast and include search and rescue, surveillance, crop and forest health, pipeline inspection, leak detection, etc., depending upon the precision of the sensor. Infrared is not visible to the human eyes, but one can probably feel it sometimes as radiated heat when its intensity is high. A thermal camera. It can hence detect areas of high temperatures. It can reveal overheating sections of electrical equipment in various devices such as switchgears and substations. A drone can help to detect these sections from a distance and increase the safety of human personnel. They can also be used for night vision and surveillance. Image sensors. An image sensor can detect and convey information about what constitutes an image. They are used in the cameras which the drones carry to create a digital image of the pictures taken by the drone. They can be used for various purposes such as thermography, creation of multispectral images, sensor arrays for X-rays, and other highly sensitive arrays for astronomy. Temperature sensors and data loggers. Data loggers are often small enough to be placed inside an insulated shipping container or directly attached to a product inside a refrigerator truck or a refrigerated container. These monitor the temperature of the product being shipped. Modern digital data loggers are very portable and record the actual times and temperatures. This information can be used to model product degradation and to pinpoint the location and cause of excessive exposure. Data loggers and temperature sensors play a very vital role in shipping vaccines, blood banks, etc. Obstacle detection and collision avoidance sensors. One of the most challenging problems in the domain of autonomous aerial vehicles is the designing of robust real-time obstacle detection and avoidance systems. This problem is complex, especially for the micro and small aerial vehicles that are due to the size, weight, and power constraints. There are multiple solutions for obstacle detection and collision avoidance in UAVs. These solutions suffer from different drawbacks. In general, the existing solutions can be divided into parts. The first part contains simple collision avoidance solutions which are based on avoiding collisions by steering the vehicle in opposite directions using different techniques. The biggest drawback of such solutions is intervention into the steering, which may not be desirable for the mission of the UAV. These solutions do not allow a UAV to control its distance from an obstacle, which may be necessary for a couple of situations. The second part can be described as SLAM-based solutions. Those solutions avoid collisions by mapping, positioning, and navigation within the map, while the positioning and mapping are based on a complex SLAM algorithm. Compared to the first division, these solutions do not limit the mission, but the collision avoidance requires the SLAM algorithm, which needs considerable memory and computational power compared to the already mentioned simple solutions because of their complexity. RTL. In RTL mode, the plane will return to its home location, that is the point where the plane is armed, assuming it had GPS lock, and loiter there until given alternate instructions. As with auto mode, we can also nudge the aircraft manually in this mode using stick mixing, that is assuming the RTL was not a result of RC failure. The target altitude for RTL mode is set using the Alt Hold RTL parameter in centimeters. When initiated Alt Hold RTL, the plane will immediately climb at a maximum allowable rate to reach that altitude. If above, it will descend in a linear manner versus distance to home, reaching that altitude at the home loiter point. RTL will command the copter to return to the home position, meaning that it will return to the location where it was armed. Therefore, the home position is always supposed to be your copter's actual GPS takeoff location, unobstructed and away from people. For copter, if you get a GPS lock and then arm your copter, the home position is the location the copter was in when it was armed. This means if you execute an RTL in copter, it will return to the location where it was armed. RTH. This mode brings your drone back to the home point if it happens to lose signal when connected to a remote controller or through Wi-Fi. With this, we'll complete our lecture on sensors. See you all in the next lecture.